In the 1940s and 50s, astronomers were measuring the speeds of stars in galaxies and the speeds of galaxies in galaxy clusters to try to determine how much mass a galaxy has. Because as a star goes around the center of the galaxy, just like a planet going around a star, the speed of that motion depends upon the mass of the things inside that orbit. So if the sun were more massive, Earth would revolve around it faster. If the sun were less massive, Earth would revolve around it more slowly, because the force of gravity moving it around would be less. So measuring the motions of stars and galaxies in clusters showed that if you count up all the mass you can see in a galaxy, and most of the mass of the galaxy is contained within stars, which are luminous, or gases, which emit light at very specific wavelengths, like carbon monoxide or molecular hydrogen and so on, which you can still measure the presence of. Luminous objects only make up about 1/10 of the total mass of a galaxy. So the stuff that we see in a galaxy, the stars, gas, and dust, is actually not even around 10% of the total mass of that galaxy. So 90% of that galaxy is made up of something else, something that doesn't give off light, something we can't see. This non-luminous matter is referred to as dark matter. Now, the discovery of dark matter was rather surprising. It means that we don't know what most of the universe is made up of. We don't know what dark matter is, and we'll talk about possible things that could make up dark matter in just a moment. But the importance of dark matter is because if we know what dark matter is and how much dark matter there is out there, or how much mass there is in the universe, allows us to calculate what the universe's fate is. The universe is expanding, and we talked about that previously. So that expansion is being halted, or slowed at least, by the presence of gravity. The stronger all of the gravity in the universe, the faster that expansion slows down and can actually stop and even reverse. So rather than a big bang, we could actually have a big crunch in the future if the universe has enough mass to cause that to happen. So there is, given its current size and the rate of expansion of the universe, we can calculate a critical density, rho sub c here. What does the average density of the universe need to be to halt this expansion? Now it turns out to be ridiculously small, 10 to the minus 26 kilograms per meter cubed. Remember, you're talking about, in kilograms, you're talking an atom, a proton is 10 to the minus 28 kilograms, an electron 10 to the minus 31 kilograms. So this is on the scale of a few atoms per cubic meter on average could actually halt the expansion of the universe. Now, of course, in our little area of the universe on Earth, the average density is much higher than this. But in the vast regions of space between galaxies, where it's mostly incredibly empty space, having one atom in a cubic meter of space, or even one atom in the size of the room you're currently sitting in, is actually pretty unlikely. The density between galaxies is incredibly low. So when we actually calculate the amount of mass that we see, even including the amount of dark matter we believe to be out there, the universe only has about 40% of the mass needed to halt the expansion, which means that, according to current theories, since the universe doesn't have enough matter or dark matter for gravity to halt the expansion, the universe will continue to expand forever. So we learned dark matter is not going to be enough to halt the expansion of the universe. But we still haven't really talked about what is dark matter. We said it's non-luminous matter that exists in galaxies and in large-scale objects, in galaxy clusters, that gives more mass to those systems, allowing galaxies to spin faster than they would be able to normally if that dark matter wasn't there. So another way of expressing that is our galaxy, the stars would fly off and fly apart if we didn't have dark matter, because that dark matter is what's holding, the majority of the dark matter is doing most of the work holding the stars in our galaxy, allowing them to spin at the speeds that we see. So the stars are going too fast in our galaxy for just the matter we can see, the luminous matter, to hang on to those stars. Now, there are two different types of dark matter that are currently being explored by physicists. The first are weakly interacting massive particles, or WIMPs. Weakly interacting massive particles are just that. They're weakly interacting. They interact mainly through the gravitational force, which is far, 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 far weaker than electromagnetic forces, strong force, nuclear weak force, and so on. So it's tough to find these things because they don't interact very easily on small scales. When you have enough of them, their gravitational contribution of all these particles combined is substantial on galaxy scales, but in a laboratory, there's just not enough to really measure any significant effect, at least with current instrumentation. They're massive, meaning that they have mass and they work via the gravitational force, and they're particles, they're little objects. We call those WIMPs. Fighting the WIMPs are the machos, which are massive, compact halo objects. Massive again because they have mass, this is gravity we're talking about. Compact meaning they're small, therefore hard to detect. Halo objects, the galaxy actually contains a halo. So we look at our galaxy on the side. The Milky Way galaxy has a central bulge, a nucleus. It has a disk where our sun is located. And then around it, at a much, much, much larger radius, is what's called the galactic halo. There are objects in the galactic halo we can see. They're called typically globular clusters, dense clusters of stars that might have actually come from smaller galaxies that were stripped of gas as they went through the galactic disk. But in addition, in the halo, you can actually have dark matter as well. So what machos are thought to be is maybe black holes or some other small, dense object all orbiting in this galactic halo that we can't see because they're small and far away. There's still some experiments we can do to test or put constraints on the existence of these machos, mainly through gravitational lensing, which we talked about in an earlier video. And astronomers think that machos really don't make up a significant fraction of dark matter. Experiments over the last few decades have limited the amount of and the type of object that these machos could be. So WIMPs seem to be the winners in the fight between WIMPs and machos. These weakly interacting massive particles are thought to be the primary component of dark matter. Unfortunately, again, they only act via gravity, so it's incredibly difficult to see if these particles are real. They're not the particles that you and I are made up of. These are not protons, neutrons, electrons, or neutrinos, or photons, or any of the other exotic types of particles we talked about, hadrons, bosons, leptons, and so on. This is something different. We don't know how these particles are made, what they're made up of, how they exist, because they only interact, it looks like, via the gravitational force. So in the lab, very difficult, if not impossible, to detect with current technology. The search is on to try to find the existence of these WIMPs and particle accelerators and so on. So work is still being done to try to identify what dark matter is. We do know that dark matter exists, we just don't quite know what it is yet.